Hello, everybody. Welcome to the introduction to and BIM picking studio training. My name is František Takac, and I'm a strategic partners manager in Photoneo. And I'm here together with my colleagues, Anna Klianova, Michal Angus, and Patrick Vakita, the BIM picking studio specialists. It will be our honor to present you with industrial 3D vision and robotic intelligence for your automation projects, BIM picking studio. I would like to say that attendees are muted during the whole training, but please do not hesitate to type your questions into the Q&A section in the Zoom panel. Questions will be answered in the Q&A panel or during the training. Few words about Photoneo. Photoneo is a leading provider of industrial 3D vision, AI-powered automation solutions, and robot intelligence software. Since the foundation in 2013, the company's mission was to give vision and intelligence to robots all over the world so they can see and understand with a clear goal to automate monotonous and risky tasks by employing vision-guided robotics. We have delivered over 3,000 solutions worldwide, and our technology was recognized by the highest honors, including the Vision Award in 2018 and Platinum Innovators in 2019. We have headquarters in the Central Europe, in Slovakia, Bratislava, with the branches in USA, Kentucky, and China, Shanghai, covering Asian market. Globally, we employ more than 200 people, and we cooperate with more than 50 distributors, which can provide you with sales and technical support. Photoneo is constantly developing hardware and software capabilities in order to bring robotic eyes and robotic brains to push the limits of flexible automation to completely new level. Our research and development teams are always looking for new approaches, how to improve already cutting-edge technology in order to offer our customers the best 3D vision and robotic intelligence. So when we look at the 3D vision guided robotics, and we try to define what is the 3D vision guided robotics, the definition is basically simple. A robot that should be equipped with a sensor or camera, and if you do so, your robot should be able, with involvement of certain vision algorithms, to move towards the target. The growing need for smart automation has caused that 3D vision as an integral part of vision-guided robotics has continuously been expanding into new markets. Gradually, the 3D vision has entered application areas such as robotic guidance, BIM picking, advanced object handling, depalletization, path correction, assembly, quality control, inspection, or shape evaluation. Photoneo has the capability to solve these applications with in-house developed hardware and software, offering customers the most complete solutions for the most advanced tasks requiring 3D vision. Now I would like to present you the entry-level product of Photoneo, the Foxy 3D scanner. The Foxy 3D scanner by Photoneo is your go-to scanner when you are looking for high resolution and high accuracy scanning of static scenes. Its structured light projection approach provides output in the form of precise point clouds for fast localization of any desired part. The robustness of the scanner ensures superior quality of scans, which makes it best scanner for even the harsh environments. Foxy 3D Scanner was awarded by the Vision System Design Innovators Awards Program for its unbeatable performance and best-in-class resolution-to-speed ratio. Each scanner from the Foxy family, the model XS to XL, is suitable for different applications, depending on the size of the scan object, scanning volume, and other aspects. You can equip your robot with a powerful 3D vision and allow it to see. The scanning volume of the Foxy 3D scanner family ranges from 15 centimeters up to 4 meters, allowing you to scan large as well as small objects. You can get 3 million 3D points in every scan across the different models. Our advanced methods for ambient light suppression provide superior quality of scans, even in most demanding lighting conditions of up to 20,000 lux. Thanks to its low weight of less than 1.5 kilograms, the Foxy 3D scanner can be mounted directly onto the robotic arm. This is a very handy option if you need to scan a big bin with a smaller scanner from variable viewpoints or to get a detailed look at the bin corners. You only need a single cable to get both electric power and data connection, the power over Ethernet. Currently, the flagship in Photoneo production is the MotionCam 3D. But actually, what is the MotionCam 3D? The Photoneo has developed and started to sell the world's highest resolution and highest accuracy area 3D camera for dynamic scenes since the last year. This device is your go-to device for application requiring fast and robust 3D acquisition. It can reconstruct accurate point cloud of various objects in a high level of detail without any compromises on quality caused by vibrations, ambient light, or motion blur. This device is your ideal 3D vision companion for handling objects in motion. So with new Photoneo patented technology called parallel structured light, we bring the state-of-the-art quality and resolution of structured light scanning into the 3D reconstruction of highly dynamic scenes. This novel patented technology uses a clever sensor design which performs the acquisition in one snapshot as opposed to the sequential scanning of a standard image sensor. This means that the parallel structured light method practically freezes the 3D scene in time. Our motivation is transforming the experience and knowledge from projects delivered by Photoneo into a product that enables our partners to deploy robust and reliable bin picking applications. And this is all allowed by Bin Picking Studio. Photoneo is also offering multiple localization approaches for different industrial areas, such as general industry, machine tending, plastic industry, foundry, logistic industry, and parcel handling, or even the apparel industry. In Photoneo, we believe that the best outcome coming from the 3D vision guided robotics applications lies in the close cooperation with robotic integrators and our customers. Therefore, we always want to express the possibilities, but as well limitations when it comes to the customer requirements on the bin picking application. After attending this BIM Picking Studio training, you will have a unique opportunity to get a BIM Picking Studio demo package for a special price. This will unlock you affordable access to experience and test the Photoneo hardware and software for BIM picking, but also other pick and place applications. A demo can be used for any type of feasibility purposes, presentations, etc. We can unlock this demo system whenever you decide to upgrade it to a full version for your production and your project. Now I'm handing the word to my colleagues. They will present you the BIM Picking Studio and will give you the training and will explain all of the functionalities of the BIM Picking Studio in details.
Okay. Hello, everyone. So, thank you, František, for brief introduction of Photoneo. So, we will start this training for BIM Picking Studio version 1.6. So, let's look at the schedule for today. There will be a presentation for whole BIM Picking Studio, how to set it up and prepare for the production. In the middle of the first part, there will be around 10:30 will be a coffee break, and then we will continue. Around 12, we will have a 1-hour break for lunch, and then we continue with the training. Of course, during the whole time of the presentation, feel free to ask your questions in questions and answer panel. If possible, we will answer it. Also, we have a Patrick here that will help us to answer some of the questions.
I can just add that we will always try to explain everything in the presentation, and after the presentation, we will skip into the BIM Picking Studio. So the training will be more interactive, and in the second part, we will do the vision system calibration. So it will be very exciting.
Yeah, we will use the robot that is behind us to demonstrate the power of the BIM Picking Studio. So we'll set up whole solution, and we will pick these parts from one BIM we have here to another that is nearby. So we will see whole solution, whole BIM Picking Studio solution working as it is. Okay. As you can see, the BIM Picking Studio is a web-based application, and when we finish our setup, this is the deployment page and the visualization of the final solution, how it will look at the end. You can see on the picture on the right that there is visualization of the environment of the robot, the bin, the different coloring of the parts that represents the path planning. You can see the waypoints for the robot there and the whole trajectory. You can visually check it, all aspects. On the right, there is on the left, sorry, there is this log panel where you can see what is happening, the localization starting, ending, picking of the objects, etc. In 1.6, we also added this cycle time table where you can monitor your cycle time, and by you can see with adjusting of some of the parameters how it performs better or worse. So this is what we get at the end of the training, the full visualization of our solution. Our motivation is to provide reliable software where you can do your applications very easily. The whole software of BIM Picking Studio is very intuitive, and you don't need to possess any extra knowledge. If you are expert in robotics, you can do it even without the training. Everything is explained and visualized. So also our motivation is to get as much information to our customers, and also get some feedback on the applications from them. That's why we have a BIM Picking Studio 1.6 now, because we gathered a few requests from our customers and implement them into this new BIM Picking Studio.
Yes, on one hand, we have very experienced delivery team, which has experiences on site. And on the other hand, as you already know, we are part of the support team. And as a support team, we receive a lot of tickets about the BIM picking, how to setting up it the most optimal way. So all this knowledge, all these requests from our customers, we are consulting with the developers, and they are trying to really find how to improve BIM picking to be more customer friendly and easy to set up.
Yeah, as we mentioned, the BIM Picking Studio is a web-based application, so it's accessible also from a remote device. Most of the things there are visualized, so it's easy to set up. As I mentioned, no programming knowledge is required. You can also copy parts of it to another solution. So if you have one solution really well set up, you can copy parts of it to another solution if you want to change the bit and keep the previous one. There are benefits that we support a lot of robotic brands, and you can also have multiple scanners in one system. We support up to 4 scanners in one vision controller. Okay. So the BIM Picking Studio has a really high success rate. The parameters you place there can help you with oriented placing as well.
Yes, vision controller can run 24 hours per day, and when you set up, when you find really optimal settings, you can go down to 5-second cycle time.
Yeah, it depends on your solution, on your pick partner, also robotic brand. So this is the vision controller. Is it made computer where the BIM Picking Studio is installed, which you received when you order the application. As Francis mentioned, it's also part of the demo unit because the BIM Picking Studio is installed there. The computer is otherwise locked and protected by password, which means that we already installed all necessary software there. You just need to plug it and plug in all necessary components. It's a computer, so the monitor and the keyboard and mouse, and then robot controller, scanner, and there is also place for network connection to the internet. As mentioned, you can access it using some remote access.
So everything is marked on the vision controller, so it's easy to set up.
Yeah, it's not shown on this image here, I think. No. But there are specific labels that here insert robot cable from robotic controller, here insert the scanner, and here's the port for network. So it's very convenient to use. Here is the picture from the opposite side where we can see the other ports. There is also a lot of USB cables, USB sockets available, so you can plug in everything you will need for your work. Okay, so for beam picking studio to work properly, as mentioned, you need the vision controller, which contains the software, and then you need Foxy 3D scanner to actually scan the parts for you to be localized in the engine. So the whole topology consists of 4 parts, at least 4, the minimum. Is the vision controller, Foxy scanner, robot controller, and the robot itself. Of course, as mentioned, you can have more than one scanner connected to vision controller via switch, and then you can have the vision controller connected via other means to another PC, which can be controlled. The data from the scanner are used to generate the point cloud, where the localization engine is searching for the parts you want to find there. This information is get via a vision controller to get the information where the part is in the 3D space, and then this information is transferred to the robot, to the controller and the robot to calculate precise trajectory, and then the robot controller will guide the robot movement.
As we already said, the vision controller is not the master. The master is the robot controller. The only thing what the vision controller is doing is taking the scans, localize the parts, and send trajectories to the robot.
Okay, so
now we will go for the configuration steps. The configuration steps means what you need to set up to have completed solution.
Here is the list of what we can see and have on the screen when we turn on the vision controller for the first time. The beam picking studio application will run automatically. So first thing that you will see is the welcome page, where you can set up your time zone and then set up your account. You can set up multiple accounts with different privileges. You can also configure this later. Then you will be asked to log in. So your solution are always protected if you use the password. So then you will see the main Beam Picking Studio interface, where you can see the solution list and all other panels. The deployment page that will take you directly to the deployment of the solution. There is also this Foxy interface, which is the interface of the 3D scanner. Then you have the network page, which is necessary to set up before you start with the beam picking, because all the communication is handled via DHCP. So we need to set up the IP addresses correctly so the scanner and the robotic controller can communicate with the vision controller properly. There is also this menu button, the 3 horizontal lines in the top right corner, which offers some additional options. There is the account management, where you can set up more accounts or change the privileges. The most important one is the documentation, where you can find also this presentation and also all necessary information about the Beam Picking Studio and all of its parts. There are also pages dedicated to each robotic brand, which will help you to set up your solution with the particular robot from the brand. Okay, so here is the solution list. There are a few things to see. The name is the name of the solution which you choose. It's for you to easily remember which solution contains what. Each solution has its own unique ID, which can be then called by a robotic program. Then you have this robot to easily recognize what robot is used with the particular solution, some other stuff, and then there is the flags. When you set up all necessary things in the solution will get this flag ready, which means that it can be directly deployed. Currently deployed solution has this yellow flag deployed. And you can also mark your solution by flag factory default. And these are the solutions pre-configured by Photoneo that cannot be deleted. They can only be duplicated and edited then. As mentioned, these actions are also available. You can duplicate your solution, like copy the whole solution if you want to keep the previous one and make some other changes or something like that. Also, if needed, you can export whole solution from one vision controller and transfer it to another, or in case of support, you can export this whole solution and send it to us. And also there is an option to delete a solution. This is the deployment page. As mentioned, when the solution is fully completed and has the ready flag, it will appear in the deployment page when you can choose to deploy it. The next tab is the network configuration, which consists of 3 parts: the robot, scanner, and the network. The network interface is the connection to the internet. It's up to you if you want to choose dynamic or static IP. The more important is the scanner interface. We recommend for a vision controller to use static IP. Just remember that the scanner and the scanner interface should be on the same subnet mask. So, for example, if we choose subnet mask 24 as our example here, it means that the first three digits of IP address should be the same, and they should have a different one on the fourth digit. Then we have the robot interface. There is the IP of robot interface, which is the IP of the vision controller. The robot controller IP, you just copy this address directly from your robotic pendant. So as for the scanner IP, the robot controller and the robot interface should be on the same subnet. So here in this example, the subnet is 16th, which means that the first two digits of IP address should be the same. It's not a different address. I see the question in the chat. The robot controller IP is the IP of the robot controller. The robot interface is the IP address of the vision controller. So of course it's different because it's a different device, but they are communicating. So they should be on the same subnet. Yeah, okay.
If you are not sure about what are you doing, or if you really try the right one IP address, you can always go through the documentation where you can find it, or you can also find this. Training material in the documentation of the BIMPP.
Okay, when you set up your IP address, there is this button called test connection. If everything is set up properly, you will receive this message that the robot is available. The next step was Foxy, so which is the connection to the web application that somehow controls the Foxy 3D scanner. There is also other application that is called Foxy Control, which also helps to set up the scanning parameters. The web interface, it's just for really quick visualization. If you have really easy parts, it's easy to set up with just the web interface. But with more problematic or difficult to scan parts, we recommend to open the Foxy control and set up your scanning parameters there. Of course, there is an option if you have troubles to setting up your scanning parameters. You can contact Photoneo support at support@photoneo.com and ask any questions about setting up the scanning parameters. We will gladly help you or try to help you. So this is how the Foxy interface looks like in the BIMPP Studio. In a moment, we will get there directly in the BIMPP Studio application. Here you can connect to the scanner, trigger the scan, even save the files in different file formats like PRAW, FLY, or PTX. It's easy. It's just simple application. So the only three parameters you can change are the resolution, scan multiplier, and shutter multiplier. The resolution has two parameters, the low or high, which can be used when you have really easy scannable parts. You can choose low resolution and it will be enough, but it depends on your part. The scan multiplier is functionality that provides averaging of the frames. So you can achieve slightly better resolution with it, but it will double or multiply the scanning time. The shutter multiplier is a parameter that is multiplying the number of frames, which is recommended to use when you have a large variant of the scanner. But of course, you can always switch to Foxy control and gain the full access to the 3D scanner. So this is how the Foxy control application looks like. As you can see, it has much more settings available to you and all the options to change and improve the generated point cloud.
So I can add that the best thing is to try first to scan with the default parameters, default settings, and when you are not sure about the results, then you can try to increase maybe the scanning time and see what if it is better. And if you are not if you are not satisfied, you can always contact our support team, and we will try to improve the scans.
The default settings in Foxy control application are set to satisfy most of the needs for scanning. Of course, if you have more, for example, shiny material, there is a scanning profile for that. And as Anna mentioned, if you have any troubles to setting up your scanning, you can contact Photoneo support.
Yes, there are two options how to mount the scanner. The one option is to mount the scanner on the robotic cell, and there is also the possibility to mount the scanner on the robotic arm.
In our example, you can maybe see that we have mounted the Photoneo version M on our cell. So we will choose this option. Of course, if your application requires it, there is a possibility to have the scanner mounted on the robot itself.
Yes. So what are the? There is a question.
No, it's not.
Not a question.
Just a reminder.
Yes. So advantages of the scanner, which is mounted on the robotic arm, is that you can, for example, if you have a really large beam with small parts, you can use a smaller scanner, so you will achieve really good resolution with it, and you will also speed up the cycle time, because the scanner is carrying during when the robotic arm is in the area of the beam, so it doesn't need to go out from the scanning area taking a scan, but it can be done in one step.
So I think now we will go to Beam Picking Studio itself and show all this we mentioned in presentation, how it really looks in Beam Picking Studio. So now we are in beam picking studio itself. Okay, so this is the solution page where we can see the list of our solution. Each one has its unit ID, the robot used, and all the flags and all the actions. Here on the bottom, we can see the news about the new Beam Picking Studio 1.6.0. So it's all listed here if you have experience with the previous versions of Beam Picking Studio. We have the deployment page. Here we can immediately choose from the ready solutions the one to be deployed. Next is the Foxy tab. As mentioned, here is the quick access to our 3D scanner. We can trigger the scan, and we can directly have a visualization of the point cloud we have. So this is our scene. We have two bins near each other. One is filled with parts. We will try to beam pick today. As mentioned, there are only three basic settings we can change. So resolution, scan multiply, shutter multiply. We can also check the texture, how it looks. So yes, it's just two bins with the T fittings, and also the depth map can be accessed. Also, we can choose to save the point cloud as the different formats.
Maybe I can change the scene a little bit, but rearrange our parts. So
See that, yeah, they will appear in the other video. But yeah, so as we change the scene, immediately after we trigger the scan, we can see that we had the scene change, and we have a bit different point cloud now. As mentioned, the most important part is the network settings. We'll start from the network tab. We have selected the dynamic IP for the network interface. The scanner has a static IP and it's set. And the robot, we have the robot interface, which is the IP of the vision controller, and the robot controller, which is the IP of the robot, which can be seen in a robotic pendant. As you can see, the subnet is set for 24, which means that the first 3 digits of the IP address should be the same. You can see it's 192.168.1. Both are the same, and the only difference is in the 4th digit. All other should stay default, so we can test the connection, and we can see that our robot is available. Then we can show you the Foxy control application. So you can see the point cloud here on the screen now. So we can check if we are satisfied with the point cloud, and then maybe modify some settings. You can see are some selected profiles. There is one for strong ambient light, some shiny material default. Usually default should be enough for most of the parts, but feel free to check the other profiles if needed.
I can just add that when the parts are very simple like that, use the lower resolution, because you will lower the scanning time, and not only that, you will lower also the localization time, because the algorithm is searching through all the points in the cloud. So you can really lower it, and indeed you will lower also the cycle time.
Okay. So we can now see that.
Yes, there is a question. So the question is, which image are you showing? We can read the image name on the top right. So I'm not sure.
I'm not sure what you're referring to. What image?
But now we are in the Foxy control application, and we just trigger the scan with the scanner, so you can see exactly what the scanner can see. Yes. I hope this is the answer.
Okay, and other question is, could give the sample how to use network port. The color. Oh, you mean this one? Yeah, I just changed the default setting is the texture. So the texture from the texture page is projected on the point cloud, and you can see it like this. I changed to normals to better when we zoom in, we can better see the points of the point cloud itself. That's why I changed for normals. So this third option is the normals. You can also check this to have normal sticks, and you can see it that every point almost has its normal shown. Is this what you asked for? The resolution can be changed in this left panel. It's the problem. I know it's a bit small maybe for you to see, but here are all the three options that were in the beam picking Foxy page. So the shutter multiplier, scan multiplier, and the resolution. For example, we can change the resolution to half resolution, set the parameter and trigger the scan and see the difference in the point cloud. So the parts are quite easy, so there is less points, but still the point cloud is still quite okay.
Yes, so the Foxy control is not the scope of this training, but we can go maybe back to.
Yes, we just wanted you to show that all the scanning options can be changed in the Foxy control. That is accessible and it's in the Vision controller installed. Yeah, we understand that they are small, so I don't know how to increase or how to changes for better. So okay, we will now continue with the presentation, I think. Let's see. Oh, there was this question also about the how to use network port. I'm not sure about the question because the network port is network port is for connection between the vision controller and the internet. As you notice, we in our beam picking in our vision controller we are using the dynamic IP address, so the vision controller is directly connected to our internet, but it depends on your local network setting in your company, or I don't know how your network is set up. So it's still a vision controller, is still a computer. So as you connect your personal computer to the internet or network, similarly you can connect the vision controller to the network. So was there another question? I think. Okay, so there is a local connection to the government. I would like to ask regarding the connection. There is a local connection so that the robot and vision controller are connected in the same network. But is it that with DHCP you can have online accessing documentation, online events, so on? So the robotic controller is connected to the vision controller, and the vision controller is connected or can be connected to the internet, the network, or local connection, local network. It's really up to you. So of course you can have online documentation, but also the documentation, it's inside the beam picking. We maybe forgot to, or maybe we should show it now. So we are again in the beam picking application, and here in the top right corner you have this option button where you have the account management and so on. And here is directly on the vision controller is the documentation. Documentation where you have everything set here as I mentioned you. Every solution step has its own page here. We will get there. Every robotic brand has its own page here where you can access all the information regarding connection your robot to the beam picking studio and use beam picking studio with that particular robot. Also, you have this presentation available here. So the whole presentation is here as well. So you can access this access it even after we finish this training. So let's go back to the presentation. Also, please, it will be better if you can use for your questions the question and answer panel in Zoom rather than chat. Use chat for some info or letting us know that something is wrong and you cannot hear us, or some remarks, but it would be better if you use question and answer panel for your questions. Okay, so these are the necessary steps we need to done for each solution to be ready to be deployed. So there is a robot gripper, the object we want to pick, how we want to pick, the grasping method, the vision system, the calibration environment, and finally deployment. You may notice not all steps are necessary. For example, the grasping method has already some easy predefined step there, which can be used in most general approaches. So we will show part of these configuration steps firstly in the presentation, then we will create a brand new solution and go through each of these steps separately to show it exactly how it works in the Beam Picking Studio application. So the first is the solution page, which has 3 tabs. The only necessary field required is the name of the solution. It is up to you to choose. The solution ID will be generated automatically, and it can be accessed via robotic program if needed. And there is the attachment logs where you can see all the attachment that has been added to the solution, like all the CAD models and so on. And the activity logs tracks the recent changes in the project. Then it's the configuration of the robot. It's quite self-explanatory. You choose the robotic brand of the robot you have and the version you are using. The only noticeable thing is the status. There are 2 options, the green dot and the orange dot. The green dot means that this particular robot was validated on a real installation, probably here in our headquarters. And the orange means that it was only tested in simulations. So just to see the okay, so here are the few robotic brands that are in Beam Picking Studio. The communication is done via our robotic program. When you get the Beam Picking Studio, the vision controller, you can just email to our support that what is your version of Beam Picking Studio and what is your robotic brand. We will send you a zip file called robotic module, which contains 5 programs. 2 of them are mandatory that needs to be installed in your robotic controller, and the other 3 are the program examples. how to prepare your own robotic program. Here is the list of the supported robots in BIM Picking Studio. As I mentioned, the robotic module is for each robotic brand, and we can send it to you as a request at our support email. The whole guide how to set up your robot with the BIM Picking Studio is in mentioned documentation, as I show you with the universal robot example. We have one here. There is whole list of necessary steps to do, how to connect your robot with the BIM Picking Studio and the vision controller. There are also the example programs, really easy one. The first one is for easy BIM picking, the other is multiple vision system example, and the third one is the change solution example. So for your particular application, you can get inspired by these three robotic programs and write your own program for your specific needs.
So if you have some specific robot, you can check if this robot is already added. You can check it, for example, on our website when this specific robot is not in our list, but the robot is from the brand which is supported. Then we can add the robot to our database. And when the robot is not from the brand which is already supported, of course it depends on business potential if we will add it or not. Basically, we are supporting 6-axis robots in our BIM Picking Studio.
Yes. Okay.
So this is what we already mentioned.
I think yes. So the robotic program is requesting the scans and the trajectory, and everything is then handled by BIM Picking Studio. So okay, what we have next? So the next step is the configuration of the gripper. Here you can add your own model. The dimensions of the model must be the same, or at least as possible same as the real ones. But keep in mind that the model itself will be used for calculations of for the collision checking. So it's good or almost necessary to have this model as simple as possible, so few kilobytes, and the origin of the gripper must be in the mounting point of the gripper. This can be changed in for example, MeshLab, which is also pre-installed on the vision controller. There is a question. Is it possible, in order to ideally adjust the field of view scanning volume, can we project laser and while projecting as edges where it's mounted? Or else, how would you suggest?
Very easily, you can check it in Proxy Control application itself. But this feature is not available in the beam picking?
Beam picking controls the Foxy scanner in the interface that it has some limitation for setting up parameters, but it takes the point cloud generated and visualized Foxy control application. So you in your application you can prepare the solution, then open the Foxy control application, arrange the scene, check the parameters, make sure that everything works as intended, as you desire. As you can check in the vision system page, we will get there in the afternoon. The localization, if it's working well. If no, you can adjust the scanning profile, scanning parameters again in the Foxy control application. Get back to the vision system in Beam Picking Studio. Again, try the localization, see if everything works. And by repeating these steps, you can get the best possible scanning parameters, the best localization profile, and then you can proceed further and finish the solution. So every step we set in Beam Picking Studio can be then we can get back there and change it multiple times until the solution works as it should be or as we want it to work. Hopefully this answer this question. Okay, so back to the, hopefully this answered your question. So we are back in the presentation and the gripper. So this is the new gripper page. When you are asked by the gripper, only necessary things are the name of the gripper, the CAD file, the volumetric model will be generated automatically. So as mentioned, this needs to be as precise as possible, but the file shouldn't be too large for the calculation to be easily handled. The next step is to configure the tool point. We can mention that the tool point is the point of the gripper where it interacts or touches the big object. On the screen we have an example of the magnetic gripper. So you can see that the tool point is placed directly where the gripper will touch the part. So it's similar like in our case, we have a suction cup gripper. So if you imagine that this is our part and this is the gripper, so we want to place the tool point here where the gripper is touching the part. So I don't know if it's properly seen here. So where the gripper is touching the part, there we place the tool point. We will show this again in Beam Picking Studio as well. You can set it up by changing the numbers directly or use a visualization to move the tool point itself in the 3D space. You have a model of the gripper there, so you can easily see if you placed it properly. We use the color convention RGB for X is the red one. Of course, if you set something wrong, it can be changed again during your setting up your solution. Mentioning the gripper, there is an option to turn on the invariances of tool point, which means that, for example, in our case, we have this vacuum gripper that is quite symmetric in the, if you imagine like this is the ZX, so in ZX, so if we rotate the gripper, it's still on the same, you can only notice by the text here on the side that it's changing position. So we can use this for picking up the objects, because if we say that we want to pick this part by like this, and only like this, that this white bore mark text is facing the camera at front, then the robot will every time needs to pick the part like this, and in this case we won't be able to pick all the parts. But if we turn on the rotational invariances in the ZX, like we showed you before, then all the options now became available, so the gripper can be rotated, and we will gain more options how to pick the parts. In this example you have on the screen, there is also enabled the z-axis invariance, and the number of steps is 8. It's not a good idea to have too much steps for these invariances, because then the algorithm will have too many options from which to choose to calculate the trajectory to pick the object. So it's good to have some invariances, to have more options for robot to pick the part, but not too many.
Yes, and everything, of course, depends on type of your workpiece and type of your gripper. For example, when you have a 2-finger gripper, your invariance is like this and this, so there are no more options to pick the parts. You cannot turn it like the vacuum gripper or magnetic gripper.
It really depends on exactly your gripper. In our case, and in the case of this example on the screen, we have invariances in ZX. You can also try. We will show this directly in Beam Picking Studio in the moment. I will ask my colleague Patrick to answer this question that has been asked in question and answer panel. Hopefully he can hear us and answer that one for you.
Disable.
Okay, so the other step we will show in the presentation is the configuration of the picked object. The object we want to pick is defined by its CAD model. It's similar like with the model of the gripper. It should be precise but simple. The volumetric model is added similarly as in gripper automatically. Up to 4 different objects can be loaded in one solution, and then later linked to a vision system. These models are used for collision calculation and so on. Yeah, here we can see how it looks in configuration of the picked object. Similar to the gripper, we just name it and load the CAD model, and the volumetric model will be generated automatically for us in a Beam Picking Studio application.
So really take care about the model you are loading, that it is not quite big. And you can also check if all the areas are closed, that there are not opened areas in your model, that it really corresponds with the reality.
Okay. Is mentioned also here that the size should be low, and just make sure that the model is whole. Like on this example, you can see there is a hole in the 3D model, and it won't work well, or even won't work at all when you have a CAD model like this. So they should be enclosed, and in case there are not, the volumetric model might get incorrect, and you will have some problems later. Okay, so I think now it's a good time to have a maybe. Okay, we will see just another question.
Maybe Patrick can.
Yeah, the first one I asked Patrick to answer, and there is another question. What if our objects always same model but in many different colors? As you can know, the Foxy 3D scanner does not work with color. It generates a point cloud from the objects. The texture is, notice that it's black and white. So if we would have the beam not full the same colored parts, but each one was different color, it would have no effect on the point cloud. The point cloud would be the same. And if it's the same model, the Beam Picking Studio will work with it as they are the same color, because for it, it's just the point cloud. The point cloud is the same. The 3D shape, or how to call it, point cloud of this object and this object would be the same, even if they were a different color. It's working with 3D data, not the color of the object. And some of them are in white semi-transparent. For example, will this have any impact on point cloud? And some of them are in white semi-transparent. You mean like the object will be in some other object, or what do you mean? Or different material? Different material could pose a problem because if you imagine that this part, this one is plastic. So to set up scanning parameters for this is quite not a challenge. It's a really easy scannable material. But if we imagine that the other one was, I don't know, from copper or some other shiny metal, we would need to adjust the scanning parameters for these metallic parts. I don't know. Do we have something other parts? No. So we would need to adjust, but it would be possible to adjust the Foxy control settings. So if that we will scan both these parts, even the plastic and the metallic, with one scanning profile. And in that case, we will also generate point clouds for both of these, even they are from different materials. And this will pose no difference for the Beam Picking Studio. Yeah, the localization is checking the point cloud space for 3D object we select in our picked object panel. So it's checking the point cloud. So if the point cloud is made, it does not matter if it's from plastic or metal. The final point cloud it's 3D points in this 3D space. So if we manage to set a scanning profile that will scan well the metal and the plastic parts, even they are the same, like from the looks, the shape, then we can proceed and it will pose no difference in a beam pick. The only difference would be that the exact point cloud of plastic part and metallic won't be the same, because the metallic shiny parts, it's much difficult to scan than the plastic one. Okay. Okay, so I think it's more than 35. So hopefully everyone is back from the coffee break, and let's go through all the steps we showed you in the presentation, and now we show you in Beam Picking Studio itself. So we are in a solution page, and we will start creating new solution. So we just click on a create new. There is also an option to import one if you want to like move one solution from one vision controller to another. You can export it and then import it in the other one. So, but now we will just create a new one. So we just click on create new one. So here is the list we need to do for a solution to be complete. So as mentioned, the required field is the name. So let's call it BPS training. The Beam Picking Studio will give it unique ID. It can be called by a robotic program, and we can select an option if we want it to have it as factory default, so it cannot be deleted and changed. Then we just proceed and click save. The solution has been updated. In attachments, there is currently nothing because we did not upload anything, and the activity log is empty because we just created the solution. So that's it. Then we go to the next step, which is the robot. So here you can see there are a lot of available robots we can choose from, but we know that our robotic brand is Universal Robots, and our robot is this one. So we can just select it. You can notice that it has a green dot, which means that it was tested in our headquarters. That's it. The robot is selected. Next, we'll move to the gripper. Here we have a few gripper already available, but we will add a new one as in presentation. So we just click add the gripper. The name, so we can recognize it, will be vacuum, for example. We will browse a disk for the STL file. So it's this one. Maybe you can just open. When we hit save, it will generate the volumetry model of the gripper. And in a visualization, we can zoom it and check if it corresponds. You may notice that the origin is in the mounting point of the gripper. So here is the place where the gripper is mounted to the robot. So you can check it here that it's okay, and Okay, so and next it's the tool point page when we can change the position of the tool point. So where the gripper is touching the picked part. As mentioned in presentation, we can either use the visualization and these arrows to move the tool point in 3D space. We can rotate it and do whatever we wanted it, or we can use these fields to directly type something there and change the position. So we know that it's a section type. So we know that the touching point or the tool point on top. So we can move it like this. So the red dot is the actual tool point. Don't forget that this setup is not permanent, so we can change it anytime later if we, for example, discover that the tool point is too deep and it's pushing into the part, or it's too far away from the part, so we can then adjust it and move it according to our needs. I think I will move it a bit up. I don't know, like this. You may notice, or maybe not, that the model is not exactly as the one we are using. The end is made from I don't know, rubber, and it's dilating. So when we pick the part, it's get pushed and shorter. So that's why our model is by this length is shorter. So that's why we just place the tool point exactly at the edge of the model.
Okay, so we will avoid the collision of the gripper with the point cloud.
Let's put it 180, and if needed, it can be changed when you perform the deployment. As mentioned, there is option to enable rotational invariances. In our case, the gripper is invariant in z-axis. You may notice that the z-axis is already selected because it's usually the most common one, and the rotational limit is set to from 0 to 360, so it's full circle, and the number of steps is set to 8. It can vary from 2 to 36, but as mentioned, we want to give the gripper and the invariances some kind of freedom, so it can choose from more points to be picked, but not that much, so the calculation won't take that long. So these default settings are for our case, for the easy case to pick object and place it to another bin. It's really satisfactory. Also, there is this option to preview the tool point invariant pose, so we can check. I will just zoom it out so we can see the bottom. See that, yeah, it's really rotating. So if you have some other gripper that has some specific model details, we can see it's rotating now just by the bottom of the model. We can notice that it's rotating around the z-axis in full circle in 8 steps from 0 to 7. There is also an option if we don't want any of these 8 invariances not to be active, we can easily disable it and just have I don't know, less number. Also, we can change this number, for example, 4, and now we have only 4 invariances in 45 degrees, in 90 degrees. But we'll stick to the default 8. It's a good amount of invariances in our case of vacuum. When we are satisfied with the settings, we just hit the save button. The tool point has been updated and everything is saved. So we can save the gripper and we can proceed to the picked object. Okay. As mentioned, we can add up to four objects into BPK Studio. Adding picked object is similar to adding the gripper. Just click to add the object. We can name it. In our case, it will be fitting, for example. We can add some description, but it's not mandatory. The only mandatory thing is the cat file. So let's find it. So for us, it's this one. You can notice that the file size is 487 kilobits, so it's a really small file. Similarly to the gripper, it has only 384 kilobytes, so it's really a simple model. So we'll open the file. It's safe to generate the volumetric model. And in visualization, we can check if it fits. Yeah, we can check. Yeah, it's really our object. So we can also choose the thumbnail like this. Set the thumbnail to the current view, and when we save it, the thumbnail will be as the one we saved.
I just noticed that we just show you how to edit the gripper, but the gripper should be also selected. If you are not sure which gripper it was, then you should know that
remember the name.
remember the name, or know that it is the last one in this queue.
Yeah.
So we will just check it, and
so we set up the gripper, but we forgot to select it. Yeah.
yes. So now you can see that this step is green, and we can go forward.
That's why the green tick wasn't there, because we set up the gripper, but we didn't select it. So the solution won't put us into deploy, because the gripper is not properly set. We set it up in a BPK Studio application, but didn't choose it for our solution. So now it's selected and everything is working. So now we have this. So for the next step is the gripping points. So we'll go back to the presentation and show you gripping points there. Also the gripping points, and then we go back to the BPK Studio application to show it directly in the BPK Studio. So let us switch back to the presentation. Okay, we are back in the presentation. So, as mentioned, we can have 4 different objects in our BPK solution. In this case, also multiple gripping points are supported. This is how it will look when you set up the gripping points in your solution. There is thumbnail, so you can have a clue how the gripping point works, what is the object, what is the priority, if it's enabled and active, and how many invariances does it have. There is also an option to duplicate it, edit, and delete. The priority can be set up as well for each gripping point. It's not the priority to pick objects by that gripping point, but to pick particular object with that gripping point. I'm not sure if it was well said. Let's say it like this. When we have two parts, and imagine that we have a gripping point here, and the part is like this, and then we have other part nearby, and we have gripping point here, even if it's for this case not good example, and we will have a gripping point priority for this point. It does not mean that the beam picking studio will choose this part first. It means that when the beam picking studio robot tries to pick this part, it will choose firstly this gripping point rather than this one. It's priority for picked object, not for all picked objects. Just for you to know. So when adding gripping point, we will get a similar interface as for previous things we added. So each gripping point has its unique ID, the priority I just mentioned, and then we have a visualization where we can see the picked part and our gripper, and we can move this gripper to the part to well place the gripping point and position it as it should or as it should work. The similar convention RGB to the coloring is the same for whole beam picking studio application. So you can easily set it up using the visualization. The next step is also it has the invariance. So let's look at it. In our case, when we have part like this and we have a vacuum, so it's obvious that it will be for us impossible to pick through this using this hose. So the only suitable place for vacuum to be placed is on this radius. So we will place our gripping point here and do an invariance like this. We'll do it shortly in beam picking studio itself, just to imagine how it will work. You can also check the presentation. They are using magnetic gripper, and the part is symmetric in the whole X, so it's easy for them to create the invariances over the gripping point. It's similar like the invariances with the tool point. We want to have multiple options how to pick the part, but not that much. So the calculations are quick and the cycle time is low. There is an option also to teach gripping points. It's often used with the difficult parts or difficult grippers. It cannot be done directly. You need to run the calibration, which we will do in the afternoon. And then you can teach the gripping points that you will attach the part to the gripper as you want it to be picked, and then scan it and teach the gripping point in the beam picking studio. Okay, there is also an option to achieve an oriented placing. As you may notice, I mentioned that each gripping point and also its invariance has its own ID. So we are able to send to a robot the combination of numbers, the IDs of the gripping point. So the robot can exactly know how we pick the part. So for example, if we took our part, we can call this gripping point 1, and this will be gripping point 2, and this will be gripping point 3. So we know when the robot, we want to orient it placing, and we want it placing, I don't know, like this. When we pick it, then the robot exactly knows that, okay, I pick it like this, so I need to rotate, place it like this.
Yes, so you know exactly the ID of the gripping point, the ID of the gripping invariance. You also know the ID of the 2-point invariance. So you know exactly how the part was picked, how the robot, what is the robot's position, and you can teach your program how to place the part in the exact position.
Yes. That's the idea behind these IDs. So everything is accessible and can be used in a robotic program. Okay, so next step is the grasping method. So we will switch back to the beam picking studio and show you everything this in the application itself. Okay, so we are back in beam picking studio application. So we jump to the gripping points. So new gripping point. We can choose here our picked object since we have only one. So the first one is selected, and its ID it's already been selected. We can change, but not necessary. And now we click add new gripping point. So here we are in the interface. Immediately the visualization is giving us the model of the gripper, model of the part, and you see they even connect in some way. It's not the ideal one, but still. So now we can position our gripper in a way we want part to be picked. So let's try rotate it. So we want to pick it from the side. Yes, so we can use the numbers here or use this. So we know that we want to pick it from the side. So let's move it like this and move it a bit closer. Again, if we made some mistake or put it too much inside or too far away, we can then adjust it later after we test the deployment. So let's see. Let's have it like this for now, and let's turn on the rotational invariances. It again default is ZX 8 steps and 360 full circle. You can preview the invariance. Suppose we can see that no, this is not the good idea for us. So let's try the YX. Well, this is not good either. So let's try the third option. Okay, we are getting better, but the rotation point is not where we want it to be. So we want to move it inside the part. And like this, let's preview this. Oh, okay, it's much better. But we need to adjust it a bit more. So Okay. No. So, but we know that 360 is not good for our part, because from the bottom there is a hole and we won't be able to pick it like this, of course. So that's why we limit this by 100, just 180. So let's see how it looks now. Yeah, this is what we want to achieve. Just pick the part from this radius where there is an option for suction cup to actually attach. So, and also in this case, I think it would be better to lower the number of steps, because 8 is, I think, too much for this really small part. It would be larger. That obviously it would be better to have 8 points. But for this, I think maybe, I don't know, 5 should be enough. But let's see how it looks. Yeah. Now it looks quite okay. So when we are satisfied with this gripping point, we just hit the save, and the point is updated. We get the green tick, and this setup is complete. We will now conduct the grasping method. We will switch to presentation again, show it in the presentation, and then we switch back to the solution and show it in a Mimicking Studio application. So, grasping method. In 1.6, this page get new looks. You can now set up multiple grasping methods from 1.6 now on. Before there was only one per solution. So now you can set up grasping method for each vision system separately. It's very important to choose the correct grasping method. It consists from 5 mandatory waypoints. What is a waypoint? Waypoint is a point in space that robot's tool point will move through during the beam picking. It's possible to define point's position and the procedure that will be executed when the robot reaches this point. For the path planning of the movement, it's easier for algorithm to set a given path from these waypoints rather than calculate for each point in space all the necessary values for the robot to move.
So imagine that you have some obstacle between the robot and your workpieces. So it is much easier, for example, to define some waypoint here and then waypoint to your workpiece, then for the algorithm to calculate every time that this is some object which can be with collision with our robot. So that's why the waypoint, that's why this method is so really important, and it's good to have really good setup of the grasping method.
We can define these waypoints as using coordinates x, y, z, but it's much easier to do it using some position of the known objects. The position of the known objects can be robot itself or the gripping point of the object we want to pick. So this is often used in bin picking studio. These two points, known points in space, like the robot base and the found gripping point, because this is given by localization that find the 3D object at calibrated space, 3D space, and its position is known, so it's easy to calculate the trajectories and set up the waypoints and then calculate the trajectories using these known points in space. As mentioned, there are 5 mandatory waypoints, which you can see on the screen now on the right. So it's start, approach, grasp, the approach, and the end. The start and end waypoints are done in a robot itself. It's defined in a robotic pendant. They are usually placed above the middle of the bin, and they can also be used as a point of reference in 3D space. The other 3 is approach, grasp, and the approach. These points in space, these mandatory waypoints are the trajectory between them is planned, and there are 2 types of trajectory: the movement, joint or linear. Linear means that the 2 points will just move, and
some shorter way,
and joint movement is used for large distances.
So when you imagine it that you have some start position, for example, then you go to the approach, and this movement is curved. Then you are from approach to grasp, you're going binary down, and from the grasp to the approach binary up, and then you will go to the end point and end waypoint, also by this curved trajectory, which doesn't need to be so precise, maybe.
Yeah, the most collision happened in the bin area, so that's why this grasp should be more precise, and the movement there should be linear, so we avoid all possible collisions. When the robot is outside the bin and there should be no other objects, the path, the trajectory can be curved, because there should be no obstacles or no options where the robot can collide. Okay. So let's go to the start position. As mentioned, is a start of the bin picking routine. It's defined in the robotic controller. Usually it's the same waypoint as the end one. It's called by bin picking studio via initialization procedure. And as I mentioned, it's usually defined above the center of the beam. Then we have the approach. The gripper is moving to the position above the part to be picked. So it's prepared for actual picking. It's usually used the found gripping point offset, then that we tell the robot to go above the found part and then do the grasp procedure to pick it actually. So on the right there, you can see that type is approach. We can choose the origin of the relative offset. Mostly is used found gripping point, but you can choose the other one. The robot base depends on your application. Then you put the relative offset value in millimeters and choose the position tolerance, or if the trajectory is linear or no. You can also call some procedure if needed.
Maybe I can explain why we are choosing this offset, which is relative to the gripping point. Because when you have this part and you go, you can also have position relative to the robot. So when your part is like that, and you are moving your 2 point relative to the gripping point, it goes like that. But and when it is defined relative to the robot, it goes the same way. But when your part is under the angle, for example, and you defined this procedure relative to the robot, it will go like this, and you are not going to pick the part. So the gripping point coordinate system is in that direction. So we want to pick this part in that direction. That's why it is defined relatively to the gripping point.
Yeah.
Okay.
Okay. So yeah, this is what Anna was mentioning right now, the relative offset of found gripping point. So the coordinate system of the robot is different than the coordinate system of the found gripping point. So that's why it's good for approach to use this found gripping point in space to use for navigation of the robot. Here is the example of relative offset when the origin is the robot. So the robot, the origin is the robot base, and the z-axis is aiming directly up. So you do not have this angle from the part. So as Anna was mentioning, that's why for approach the found gripping point is better to use. Of course, it depends on the application. There can be some differences, but in our case, also we will use the relative offset, the found gripping point. Okay, so the next mandatory waypoint is grasp. Is the gripping point of object that is ready to pick.
So in this point, you can call procedure attach, for example.
So in our case of vacuum, attach will mean that we will turn on the vacuum and will attach the part to the gripper. In the case of magnetic, you will turn on the electric current to start the magnetic gripper. So we can probably move to the D approach. It's different from the previous one. So when we are approach the part and grasp it, now we want to move it. Now it's a good idea to think if it's a good idea to again use a relative offset the found gripping point, because in this case it will go like this.
Yes, and possibly your workpiece, which is in the approach, will collide with another pieces in your bin. So
that's why it's a good idea now, if you think this through, is to get out of the possible collisions. So the best approach would be to directly move it up, because we assume that the localization find a part not somewhere under, but on the top. So to move it directly up, and in this case, it's a good way to use the relative offset of the robot base, because in the robot base the z-axis is facing directly up. So this is our case. So even if our part is angled, we will go directly up and we will get out of the bin, and then we can proceed with the moving of the robot. So there is also an option, if needed, to relative to the found gripping point or some other fixed plane relative to the start or the end. And it may help when you have the part really close to the wall of the bin, and the wall is not flat, but it's bumpy or not linear. So in that case, when you move directly up with the part when they're approaching, you can hit the bin or something like that. So in that case, you can change the relative offset to, for example, the end waypoint, which if you set it up in the middle of the bin, the part will go directly to the end. I think we have a question there, so let's see. So your camera is fixed to a standard position if the field of view includes 10% of view goes out of the table, not useful. Can you drop it out in the bin picking studio?
maybe this step will be proceeded in vision system.
Oh.
When we will use bounding box to search for the objects only in our bin. So just wait to
the afternoon.
the afternoon.
Also, the other possibility in Foxy control, there is an option to set up your camera view, your field of view, which part of the scene you want to keep and generate point cloud width. So you can also prepare before actually setting up bin picking studio application to set your scene there in Foxy control application and just cut all what you want in your scene if needed. And also there is this other option if you're scanning larger volume, it does not matter, because you can set up a bounding box for your localization, so the engine will only look for parts in your pre-selected 3D space and find parts there, and do not work with the rest of the point cloud. Okay, so this would be the approach. Here are visualized the three options of the approaching. The first one from the left is found gripping point. So it's like opposite of the approach. If we approach it from relative to found gripping point, we'll go like this, and then the approach will be the same. So we'll go up there. If it's relative to the robot space, the z-axis is facing directly up, so the part will go upwards. And there is also a possibility to explain, which is good when you are picking from the deep pins. So every part will go up to the given plane in the 3D space.
Yes. The goal is to de-approach the part above the beam, because then you are sure that there are not any collision with the beam or with another parts in the beam, and then you can go to the end position.
If you set up your environment, you'll get that in the afternoon properly. The highest possibility for a robot to collide with something is inside of the bin. So you want this robot going in and out of bin as smooth as possible without collision. So that's why this is most important part of the setting up the bin picking solution. Because when the robot will collide, you cannot proceed with the picking, of course. The questions are still the. Hopefully, we answered your questions. Okay. I move back. No, this is the fixed point. No.
That's what we just explained.
What we just explained, yeah, that this is used when we have a really deep pin for us.
And another thing is when you are defining the start and end position, then the best thing to do is to define the start and end position close to the beam. So you are sure that trajectory is not calculated over the whole space, but you will reduce the space and you will save some cycle time.
Also, as mentioned, if you set your start and end position above the beam, it can be used in a relative offset point to help pick parts that are close to the walls of the beam. So here are some. So, and the endpoint, as mentioned, is usually where start is the end of the routine, and it's defined in a robotic controller. I think we can now. Yeah, there is also an option to use as a offset point. Some custom point will be defined in the 3D space. The space is calibrated, so we will do it in the afternoon, so it's also an option. Okay, so this is for the presentation now, and we will go back to our bin picking application. I will just change the sharing. Yeah, so we finished by setting up our gripping points. So let's save it. Okay, save, and let's go to the grasping method. So we have already here created some basic grasping method. You may notice that here is not green tick, because by default there is already a grasping method. So if we do not set it up there, we could deploy this solution, because there is this method as mentioned with all 5 necessary mandatory waypoints. We can go through them. So here we have start, that is we can call procedure, but we will call none. Is defined in a robotic program. Then we have the approach. For now, the default is found gripping point, and the relative offset value is set to 10 centimeters. In our case, I think that we have set up start and end position in the middle above the beam, so we can keep this approach like it is. For us, is as mentioned, the origin of relative offset found gripping point, the best variant here. Then we have the grasp, where we can call the attach, but in the case of vacuum cups, it's also a good idea to start the vacuum a bit sooner before actually touching the part. So maybe, I don't know, 1 or 2 centimeters above. So let's see, we can show it to you and use it in this grasping method to show you that you can easily add your own waypoints to these 5 mandatory waypoints. So we will add a new stage. It will be relative. We can call it vacuum. It will be origin will be again. So the idea is that we will start, go to approach, then just 1 or 2 centimeters above the found gripping point, we will turn on the vacuum. So we call the attach in our program. Then we move to the grasp. The vacuum will be on, so we will attach to the part and then go the approach and to the end. So that's why we choose the origin of relative offset found gripping point, and we just put it, I don't know, like 2 centimeters above.
About, yes. About
So
2 centimeters.
about, of course, as everything before, if we decide later that this is not a good idea or we want to change values, you can anytime go back and edit everything you set up before. So this can be also changed.
And we have to call attach.
And we will call our attach function that is defined in a robotic program. And we just hit save, and you can see that it appeared, but unfortunately it appeared after the approach. So we will just take it and move it before the grasp. So we can even edit and okay. So now in grasp, we do not have to call for vacuum because it's already turned on just before it's attached to the part. And then we have the approach. We have the default value of origin is set to robot, so it will move the part directly upwards. We can keep the 10 or
it should be about the beam, so we can So we,
Yeah, I think we should increase this value, right?
15, for example.
15. I think 10 is just the height of the bin, so we will change it for 15 centimeters. Okay. So an end is also set in a robotic program.
So
Okay, next question. From the moment of grasping and while they are approaching, in some setups we could move close to the sensor. How to ensure that we will never end up exposing the sensor? You will get there in the afternoon, but I will just point it out now because you asked. So the whole setup, like you see, there is this environment page where we can add a simplified model of our cell and place it there, and we can, and the robot will know that these things are there. If we do not, if we will open the environment now, I can show you, so it would be better to answer your question right now. If I click on the environment,
we didn't.
I didn't say, oh no, never mind. So no, okay, there is no vision. No, we need to set up. Okay, I cannot show it now.
We didn't calibrate the camera
Yeah.
within the robot, so
Normally, when you do this step by step, go grasping method and set up your vision system where you tell exactly that this vision system contains this scanner in the environment page, then you will see the robot and the 3D model of the scanner. So from the beginning, when you set up the vision system, the BIM solution knows exactly that here is the robot and here is the 3D scanner. And if you've done the calibration, the robot space and the camera space is calibrated. So the robot exactly knows that, yes, here is the scanner. So when he will calculate, or the path planning is calculated, he will avoid it. Also, then we can add this cell itself, the beams, even the wall behind, that to remind the robot that these are the objects you can collide with. So if he knows exactly in the space where they are placed, he will avoid them.
you can even create your own virtual space that you, for example, some virtual cell, which is not actually existing, but you don't want the robot to go to this space. So we can avoid the collisions, and you will tell the robot that you can move only in this area.
Yes, this better it will be explained in the afternoon when Anna will go through the vision system and the calibration and the environment itself and even deployment. So there you will exactly your question will be answered again with the proper showing in a BIM Picking Studio application. I'm not sure if we even no, it's saved. Okay, so it's saved.
Okay, so we can go to questions and answers, maybe.
Yeah.
If there are any additional questions.
So hopefully we answered your question. It's the afternoon part. It's more fun. There you will be working with the piece, with the scanner, and even with the robot. So this is more theory than application, but it's needed for you to understand how the BIM Picking Studio application works and every step that is necessary for it to work. So this is the like, I don't know, half, the boring half, and then you will have the fun part in the afternoon. So feel free to ask the question for this part. If necessary, we will answer all your questions, and afterwards we will have a, I don't know, 1 hour lunch break. And after that, we'll continue with Anna, and she will show you the rest of the setting up the beam picking studio. The second part will be without presentation, so we will only work in a beam picking studio application because everything needs to be set up there properly.
Yes, Antonio's just wrote us that every step is fun, so we are glad to hear that.
We are really glad to hear that. Feel free to ask anything about what we talk about now. Some of the things maybe seems a bit abstract, but when you see it with the actual deployment and actual visualization in the deployment page, it will make much more sense. Of course, just a reminder that this is really simple application, and every other application may be a bit different. So we need to modify. We, for example, did not modify too much our solution. The gripping points were quite easy. The gripper was quite easy, and also the grasping methods are easy for this type of application to pick one small part from one bin and place it to another.
Yes.
So it can be different, but if you would have a problem to setting up your solution, as I mentioned at the beginning, the solution can be exported, sent to us at support.photoneo.com, and we can help you set it up, the settings or this grasping method, or help you choose the gripper. We have our delivery specialists are known to come up with a solution for almost every project. They've seen a lot of grippers and have pretty much experience with them, so they can help you design your gripper for the part you are trying to pick, and so on. So there are many options.
So you don't need to really be a programmer to set up the beam picking. You have to just follow the steps and keep the default settings first. There is also the visualization, so you can be sure that your setup is you know exactly what your setup is doing. What have you done? So if you have any question, there is also our colleague who is specialized in developing. So
okay, we have another question. I wonder where define the picked object place to somewhere. This is defined in your robotic program, because in beam picking studio we cannot exactly have every possibility of picking their setup, so it's really in the robotic program.
you are not controlling the robot in beam picking. You are just sending the trajectory for the robot.
Yeah.
So if you want to navigate the robot to some specific position, you have to define it in robotic controller. So that requires some programming skills and some knowledge about the robotics.
In our case, it's written in the robotic program, just a simple command that after these picking path stages, when they are all done, the robot will move above the second bin, and we call the detach function. So it will stop the vacuum, the part will fall in the second bin, and then the cycle continues. So we'll go start, and then beam picking process, and that the placing needs to be done from the robot side. Okay. Hopefully that answers your questions. And the other question is, I guess in the TCP model, which we had to import the CAD file of it, only this was important, not the rest, which are mounted on the tool, flange on the robot or sensor and the vacuum.
So if there are some additional tools if there are some additional parts on the gripper, and you think that these parts can be in collision, for example, with another with the cell, with the beam, then it is good to have the model also of these accessories. But in general, the model of the gripper is the one you need, just simply one.
You just need to check if any feature on the gripper can be or can come to collision with something in the bin or the cell area. In our case, you may notice it's only a tube. That's why the model is so small, because it's just a tube. But there are grippers, I don't know, 2-finger, that is a bit more complicated, and the model would be a bit larger, because it's not just the tube. But since all these parts, you can see that there are some smaller parts, but those are not necessary, because we can make a simple model even out of this. But we do not have too much grippers in possession here, so we can show you the difference or how the models will look. But some balance between the simple model and the model with as much detail as needed for proper collision calculation.
Okay, it's understood. I like your questions, Antonios.
Okay, so hopefully this answered also these questions. This question.
Of course, there is also space to have a questions in the afternoon.
Yes, if there are no questions for now, we can have the lunch break.
Yes, so we will be back in 1 hour.
So now it's 11:45, so we can 1 hour is okay.
Yes.
Hopefully for everyone, and then you can think what you learned here through, and maybe ask about this first part again after the lunch. And there may be more questions after you see Anna performing with the vision system calibration and all the other stuff needed in beam picking.
Hello, we are back again. So I hope that all the participants are present. And as you already know, today agenda is the beam picking version 1.6, and we are going through the vision system, calibration, environment, collision avoiding. We will look into the settings, and we will start deployment, and we will show you how the inspector is working. So I hope that you have a good lunch and that we can start. Okay, so we already proceeded all these steps like solution, adding robot, adding gripper, pick the object, we define the gripping points and grasping method. So now we are going to the section vision system. In the vision system, we will create localization profile. What is the localization? The goal of the localization is to determine the position and orientation of the object within the 3D space. So you need the 3D data, which are captured by the scanner and represented by a point cloud. Then you need the CAD model of your picked object. So the algorithm uses the precise geometry of the model to recognize its position. We'll start vision system by clicking. We'll add a new one. We will fill the mandatory fields like a name. So the name can be Vision System 1, make it simple. The scanner ID, we can check aviable scanners, and there are a lot of them because we are on our headquarters network, but I know that my scanner ID is 1709004. So that's the ID of the scanner, but if I'm not sure, I can just check on the back side of the scanner. And the scanner model, our scanner is M. The scanner mount position is on the robotic cell, but there is an option robot flange. The picked object, we already added the T-fitting. There is no other option. So now there are two options. We can create a new profile or we can upload existing one. So as we don't have already a localization profile, we will create a new one. So it will take some few seconds. We will start locate. So the scanner triggered the scan. We already have the point cloud, and as you know, the objects we are searching for are these T-shaped plastic workpieces. The first thing to spot is different colors. The gray one is for the background, and there are different shades of green. These green bars, or this point cloud, is divided into the green segments, and each segment is potentially our search object. So this segmentation is the key parameter to have really successful localization. So we have a right part of right beam and left beam, but we are going to localize objects only on this right side. So what can we do? We can also enable the bounding box. This one is really huge, and this bounding box will define the area in which localization will be provided. So we can just change the size by grabbing the arrows, and maybe this is too big still. We don't want to have a big area to search for the objects. We want to save some computation time. So it's still not enough. It's rotated, so we can rotate the bounding box. Okay. We can resize it a little bit. And I think it's just okay. So when I click on Start Locate, you have to wait a few seconds. You can see that only parts which are localized are in the area of the bounding box. There are different options like view. You can choose top view, bottom, left, as you wish. there is a point cloud that if you don't like this green segment, you can, for example, use the black color, and you can also choose the point size. Maybe it's too big, but we can scroll on some parts, on some work pieces, and looks if the point cloud and found objects, if they really fit together. So I will go back to segmentation because I like this shades of green. Another thing to see is this table. We can see that localization was able to found 31 objects. Each object has its unique ID, and another parameter is the overlap. You can just click on it and just analyze which part is which and what is the overlap. The overlap means how much the localized object match with the point cloud. So the overlap is really high, as you can see, but there are also parts which overlap only 23%, and maybe some parts are not found because they are in strange position, or maybe some of them are turned. Maybe this one. But we will tune it with selecting the right parameters. So the first parameter is timeout. It's the total time when the localization is taking scan and searching for the object. When we click on the localization, I will click Start Locate again. Then maybe localization is able to find parts maybe in 5-6 seconds. So I can change it, or maybe I'm satisfied with this timeout. The overlap, it says how much the part of the visible surface match with the CAD model, but with CAD model of our workpiece. So when you set up 15% overlap, which is default value, it means that at least 50% of the visible part of the point cloud needs to match with your object. That's a really low number, and if you keep it low, then it can happen that your part will be flipped or strangely rotated, and you can see that most of the parts has overlap over the 60%. So we will change it to 60. Okay. So 24 objects were found, which is still a very nice number. These two pieces are not localized because, as you can see, they have the same shade of green, so they are supposed to be as one segment. But if you need better segmentation, for example, you can use the parameter which is called scene clustering level, and there are values as low, normal, high, and very high. So we have simple small parts, and default value is normal, so maybe we can change it to high. And we can start locate and see if we can localize one of these pieces. No, they are still stacked together. but it doesn't matter so much. Another parameter is matching algorithm. When your surface, when your workpiece has a smooth surface, you can use matching algorithm surfaces. When you are searching for example, some sheet or cardboard or something very flat, you can use edges. And when your workpiece is quite complicated and it has also the smooth surfaces and also some edges, you can use combined. So we will try to use combined algorithm, and maybe it will performing a little bit better. Yes, and now you can see that these two segments are recognized. I think that our localization profile is quite good. There are some advanced settings. Maybe we can go through them very quickly, because in general, when you have some new use case, please try to use firstly default settings, default parameters. Just look on into the table, see what is your overlap, and maybe choose higher value, because 15% is really low number. You can change the scene clustering level when you have small, really complicated parts. And you can also assume which matching algorithm is the best for your part. There is global maximum feature fit overflow. This parameter, what is the overflow? So imagine that you have some very flat, for example, flat surface, and it can happen that part of the segment, part of the point cloud is also, there is some background which is part of your point cloud. So this is what we call overflow. And now the global maximum feature fit overflow is 20, which means that 20% of the objects can be the overflow. So now our scans are really nice, and the segments are really nicely separated, and the overflow is 20%. Of course, we can go to lower values, but as the localization is performing fine, we can leave it like that. There is also model key sampling. So the default number is medium, but when you have a very complicated part with a lot of edges, with a lot of details, you can use a dense parameter. And when you have very easy thing like a box, you can use sparse. So you will save also the localization time with this parameter. So another one parameter which can be useful for you is projection hidden parts tolerance. So for now it's 100%, but you can, if you want to see only parts on the top, then you can choose the lower number of projection hidden part tolerance. But as we have a small beam with one layer, it doesn't matter so much for us. So if you are interested more in these advanced parameters, just let me know. We can go through them in more details. But I think I showed you the ones which are really useful. As you already noticed, that parts are rendered in different colors. The golden ones are unoccluded objects, and blue, the objects which are rendered with blue color. They are partly occluded, as you can see here. Of course, they are partly occluded in the view of the camera, from the view of the scanner. So if we are really satisfied with this localization profile, we can save configuration. So the localization profile is successfully uploaded to Vision System. The PLC file is created. We will quit localization and we will save this Vision System. So another thing you can see here is calibration metrics. Of course, that when you are triggering the scanner, the parts are localized, but they are localized in the coordination system of the scanner, and robot needs to know where the parts are from the coordination system of the robot base. So to find the transformation between the scanner and the robot, you need the calibration metrics. For now, we didn't proceed the calibration, so this matrix is empty for now, but when we will finish the calibration, there will be numbers which are representing the transformation between the calibration, between the scanner coordination system and the robot-based coordination system. So we will save it, and you can see that we added the Vision System. Of course, that you can have multiple vision systems. You can have multiple scanners. You can have a multiple scanner position or picked objects. And for each combination, you need to create a new vision system. So our use case is quite simple. We have only one scanner model. We have only one picked object. So one vision system is just enough for us. So we will continue with the calibration. So as I already said, you need to know what is the transformation between the scanner and the robot-based coordinate system. So what we need for calibration is the robot, of course. We need the scanner, and we need also the calibration object. The calibration object for the suction cup is a ping pong ball. It's really easy. Maybe you can ask why, but ping pong ball, you can buy it everywhere. It has a very nice smooth surface, so it is easy to scan. And of course, that we are using the scanner M. So for the smaller scanner, we are using like the scanners as XS, S, or M. We are using this ping pong ball. And we have for the larger scanners, which they have a larger scanning volume and lower resolution. We are using larger balls. This ball is really easy to attach to vacuum gripper, but of course you can have a very complicated gripper or big one or two-finger gripper. So for this occasion, we have a special special tool which is easy to attach to the gripper, and the ball is on top of it. So during the calibration, we will position the robot to the different position inside the beam area, and we will scan the ball. Beam picking will evaluate the exact position of this ball. As the robot is communicating with the vision controller via network server, we also know what are the position of the robot. And within this information, we can calculate this transformation matrix between the scanner and the robot. So there is a question: does the ball need to be placed where the TCP is? Yes, the ball is mounted. Not exactly. When you have 2 fingers, you will attach the ball, for example, to this position with this special tool I told you. Unfortunately, I don't have this tool with me, but imagine that with 2 fingers it is like this. Of course, you can use any ball you have. You just need to know the diameter, the dimension of the ball, and you can enter the custom ball. But you need to remember that ball needs to have a nice smooth surface, so the algorithm will be able to calculate, to evaluate the position of the ball. So I hope that I answered your question. Okay, Stefan, great. I can show you this tool I mentioned. This is how it looks like when you have a gripper, for example, 2 finger, then you can attach it on the gripper like this from this side, and you just need to position the robot that the most of the part of the ball is visible on the scans. Okay.
Maybe just to also mention that when you order a beam picking studio, you will receive this tool with it.
So calibration will need 4 points, but this is the bare minimum for successful computation. So when you are a regular user, you will need at least 9 points for the calibration. So maybe enough talking, and we can start calibration. So you can see that we can select the ball. There is a ping pong ball, which is this one already, but there is a snooker ball with a larger diameter for the larger scanner, for L or XL, or you can use a custom ball. So I will use this first one, and what I need also is to remove the beads. I will attach the ball just here. So we attach the ball. So remember, that during the calibration, try to move with robots that you are not going to move with the ball, because then you have to calibrate again. So, so there is a question. Are there instructional videos of this calibration model available in the Photoneo cloud somewhere? There are some. Yes, there are some instructional video which are also describing how to proceed calibration the best way. When you are not sure about it, if you position the ball right or anything, you can always write us. We will answer your question within 2 hours. So I will go back to beam picking studio, and then I enter select ball. I remove the ball, the beams. I move the ball on the gripper, so I can click on proceed. Okay, the calibration process has been started successfully. So you can, there is a scene. This is how it looks like. This is what the scanner can see when the beams are removed, and you can just add the calibration point by clicking on add. As I have a collaborative model of the robot, my colleague just pushed the button on the robotic pendant, and I can move the robot into the first position. I will move it into the corner. I will click to add calibration point. So when the calibration point is added successfully, there is a green notification about it. We can move a little bit this position. It is slightly different. I really move with the robot, and when I add calibration point, there is a red notification that translation of the added point is not sufficiently different from the other points. So it means if the previous position of the robot and the ball is similar to the current one, you will see this notification. So I will move robot. I'm trying to turn in all the joints. So I will find a different position and calibration point. Okay, this one was added. This one was different. Then I will move robot to another corner. Okay, it's partly it's really good that we get it, so we can move it differently. For example, here do not hit the ball. Okay, the ball is visible. The position is different, so another point is added. So we will try another corner of our scene. This is also a good one. So for now, you can see that red notification says that unable to detect the ball. Please try to change robot position and try again. Of course, the ball is out of the scanning volume, so we'll have to move it a little bit closer and under the scanner. So I will just move it to the scanning area. Okay, this point is successfully added. We have already 6 of them. So it's going really great. Okay, the calibration point cannot be added. Only 28% of the calibration ball surface is visible. So we have to move the robot so we will see the part of the ball, larger part of the ball. So maybe this position will be sufficient. Right? Then this position will be good enough. Okay, to this A point and the last one, I can move to the center of the beam. Like this. And I will add calibration point. I hope it will be successful. Yes, and the calibration accuracy is 0.2 millimeters, which is in our case of the robot, and the accuracy of the scanner is just sufficient for us. If we are not sure if the calibration is okay, if we need to decide if to add some additional point, so we can go to the verification and we can just check how it looks like. There is a question for us. I was expecting the accuracy to go lower, below 1.1 millimeter. Yes, maybe with why do more points the calibration accuracy higher and higher? Yes, so in the table you can see each calibration point and its accuracy. So some of them are higher, some lower, but I don't recommend to deleting when they are below the value of 1, because this will affect also the accuracy of another points we just added. So maybe we can improve it a little bit with another points when we will really rotate all the joints of the robot. But with the accuracy of this robot and the scanner, I think it's the good one.
I think that the question is that the accuracy in the table is not accuracy, like overall accuracy, it's the accuracy of each point. That's why it differs, and it looks maybe it goes higher, but it's the accuracy of for each point. In that case, we can recognize maybe one of the point has similar joint values or was very close to another one, so it has higher accuracy, lower accuracy, so we can delete it. So in this case, we can check the overall points. Each one has similarly accuracy in the order of 0.1 millimeter, and the final accuracy is the one that is on the upper side of the screen, the calibration accuracy, millimeter 0.225. It's not overall like for 1.035 or 2.012. So it's for each separate point.
I hope that it is clear. And if not, we can go back then to this question. So as I said, we can go to the verification of the calibration. So you really can see if the model of the robot and the point cloud which was captured by the scanner, if it really matched together. So you can just really zoom in and check it. You can see there is some inaccuracy in it, but for our use case, it's just sufficient. So if we are satisfied, we can finish and save result. Of course, if you have multiple vision systems, you need to make multiple calibration with each vision system separately. Maybe it sounds that it can be quite boring, but in new version 1.6, there is an example program. You can find it in robot module, and it is called at calibration point. So you can define the position of the robot in the space of the beams. You will attach the calibration tool, and you will just run this calibration through the beam picking studio, and this calibration will be automatically done. So you don't need to move with the robot. It's much easier. So I hope that this section is clear enough, and maybe we can move to another section, which is called environment. This section environment is not mandatory, so there is no green tick. But after the calibration, there is already here the scanner and your robot in the zero joint position. So first thing I'm going to do is I will go to the vision, and I will connect to my scanner, trigger the scan. Okay. I have to move my robot. Okay. So I moved my beams back. So I triggered the scan, and then I can see there is point cloud. So this point cloud I can use as a guidelines where where my robotic cell is, and I can use the guidelines to add another object. So I will go to the scene. I can add objects, and there are multiple options like upload STL, so you can create your STL files of the robotic cell of the beans in any graphical software. You can also make your own box or another objects from this section. But I already have my cell here, so I can just draw, and I need to choose demo cell generated. So I will call it cell very simply, and the type is environment because the cell is part of environment, and I will upload it. So it looks quite good. That the robot is positioned as it's in reality. And also it looks okay. So I will upload the beans. There is the left bean, so I will call it bean L, and the type of the object is bean. I will upload it. So I have my left bean uploaded. Okay, then I add another object, is the right bean. I need this one, so I will call it bean right, and the type of the object is bean again. So I will upload it, and I can check if it match with point cloud. It's a little bit shifted, so I can click on it, and maybe I can move it a little. Maybe robot shouldn't be visible right now, so I can move it a little bit. Now it match maybe better. Move it a little bit more. Maybe it's like that. Okay. And okay. Okay. My robot is back. And maybe there is a small rotation. And if I really need, maybe this is great. Okay. So I'm satisfied with it. And I will also, as you can see, there is a ball. So I don't want to hit the ball behind me. Okay, I will just check. Okay, I don't need to see this axis for now. And there is a question. Is it possible to see the actual robot joint stays in real time in environment? Of course, you can enter the actual joint position, and I will just continue and what you see. I will just move the robot to the start position, and we can check if the start position really match with our environment. So thank you, Stefan, for your question, and you will see it in the next step. Okay. Okay, we can continue. So I can add a wall behind the scene, some thin wall. And my wall is a little bit higher, like that. And we'll change depth, that, and we will just grab the arrows and move it. Yes, so a little bit more maybe. So I can check, yes, maybe this corresponds with the reality. And we will call it wall. Okay, so another object is added. And another thing I can do is I can protect the scanner from any damage from the robot. So I can create another virtual object, and I will let it name box because it will be box, and the type is virtual collision object. So it's the object which is not actually existing, but it is good to have it. So I will just make this object smaller because it's quite big. I will move it slightly. The right position. Maybe like that. Okay, looks good, but it's too small. So I think I have to change the width of the, so maybe 800 as too big. I don't need that. So 600 millimeters. So I created some protection box around the scanner. So this will be collision objects for my robot. It's a little bit bigger than my scanner. I can just put it down a little bit. So I'm sure that my scanner is 100% safe. When I'm satisfied with it, I will save the scene. So this part is done. Can go to the robot. There are a few options what we can do. Maybe it will be your answer for Stefan. So what can I do? I can really move with the robot to, I can use 2 coordinate space, or there is also the robot base coordinate system. So I can just move with the robot and see if it can reach the beam. what I will do now, I will move the robot exactly into the start position of the robot. You can just read it from the robot dependent, and I notice these numbers. It's 0, minus 1.57, minus 1.93, minus 1.15, 1.5, enter. And this is really the position of the scan of the robot, which is in the start position. Of course, that you can move the robot, for example, under the scanner. You can read its position or in a robotic pendant, and then type the joints here and see if it's match. So then I can just I can see what is the reach of this first joint. So as you can see, this is the first turn, another turn. So robot is able to do 2 full turns. It's really too much, and it's crazy because we want to move robot from one beam to another. So as you know, the algorithm will calculate all choices the robot have. So I want to save some cycle time, and I will set join limits. So the start position of the first joint is 0. So maybe I can go to degrees because it's much easier for me to imagine it, and I can set the joint limits, for example, from minus 120, for example. I can simply type it here, 20 to 120. So a robot will move with 240 degrees, and that's quite enough. I will save it, and now the robot's joint limit setting have been updated. So now when I turn with the robot, yes, it's from one side to another side. It's the full 2 turns, which you can see before, they are not enabled. So this is my joint limit I want to keep. Of course, that you can, for example, create a cell around the robot, and but if you want to have really short cycle time, if you want your algorithm do not calculate for the whole volume, for all choices the robot has, it is much better to just add the joint limit and think about it, what the robot can do with it. So we can go to the tall coordinate system. I will zoom here. So I will just check if my robot is able to go to the different parts of the beam. And here is the collision, but yes, it is really possible to reach the parts here or here. So it looks that he can really work with these settings. Okay, So I think, yes, this was saved. This is done. We added the scene, we added the robot, we enabled here the vision system to see where the point cloud is. And our environment is done. I can go to the settings. In general, when you are making your use case, you can really tune most of the things in the previous steps, and you don't need to really touch the settings. So if you are making your first solution, please do not change these default numbers. Maybe only thing you can be interested in, that is this picking priority. So you can choose your picking priority method. It can be a closed point of located objects in given direction, or centroid coordinate of localized objects. So you can say if my localized object is really close to the robot, I can pick it as a first, or you can choose overlap of localized object with model if you want the overlap to be these parameters, this parameter which will help you to pick the first object, or there is number of collision with prefer. So I will keep the default setting. I didn't change anything, so I don't need to save it. And all the steps are done. So our deployment has a green mark, and we can start deployment. So you can start the deployment directly from here, or you can go to solutions. You can start deployment from your solutions, or you can go to deployment page and find the one which is preferred. So I will go back to our solution, and we can test it how it is working. So I will click on deployment. Everything is set up. I can click on start. So we will start our robotic program on our robotic program pendant. We will move the robot to the start position and wait for connection. So it will take a few seconds. So the objects were scanned, and the objects were localized. Now I can zoom it.
So if you are asking why it's so slow, it's why we put the robot on slow motion. So it's just 25% of speed. So so it can go faster. But just to show you the process, how it's going slowly to really see what's going on in deployment. That's why it's so slow. We will make it faster in a minute.
We can pick some objects so you can see that can you see in deployment it really match what can you see exactly what the robot is doing. So now it is going to de-approach, and then by joint movement to end position, then deattach the workpiece, and another path is already planned. So now it's going to pre-grasp. You can hear that the vacuum was activated. Now it is going to deattach, de-approach, and from de-approach to the end position. The new scan is triggered. The parts are localized, and another part, another path is planned for this workpiece. So as you can see, some of the parts are different color. The green one are ready to pick workpieces. There is also the brown one when the grasping angel was rejected. So there is a red one, which is bad because the waypoint computation failed, and the blue one is one which is picked. Okay. So we can stop solution for now. And we will stop the program. So, and there is a question: why did you set the start vacuuming before reaching final destination target? So why we set to start vacuuming in the pre-grasp? If you remember, we can also call the attach in the grasp, but our vacuum is not so fast when we need the vacuum really be efficient and strong enough to grasp the part. So why we define the pre-grasp this point when we call the procedure attach to start the vacuum, which will need just maybe 1 second or 2 to start, and then we go to the grasp when the vacuum was already working, and we are sure that this vacuum can really grasp, is strong enough to grasp the object and pick it. So that's the answer on a question. And then there is another question: what can we do if we have problems during the path creation? The question is, what do you mean by the problems? Because each use case differs. There can be multiple troubles with, for example, issue connected with the objects. For example, some objects are not good to scan. For example, they are too shiny, so the point cloud is not so nice, and the localization is not able to really recognize the object in the scenery. So maybe there can be issue that you really need to tune your scanning profile, or so for example the localization needs to be really tuned, because some of the objects can be, for example, flipped or moved. So there are a lot of later steps that can fail the path planning. Yes, this is choosing object to pick timeout. The path planning failed, for example. It can happen, for example, that the localization needs more time to find an object, and there is no time for path planning. So then there is an error message for timeout. So you can prolong the time for the localization, for example, in this case, or you can define it your robot program when there is a command which is called wait between taking the scan and the localization. So this is what can you do, but of course it depends on situation. So I hope that this is what were you asking. So we can go back to deployment. So as we already said, that you can see the different colors of the parts. The blue one is one which is already in the process of the picking. The green ones are ready to pick, so they will be picked. One of them will be picked in the next turn. You can see that there is a brown one, and grasping angle was rejected for some reason. And there is the red one, which is the path planning failed because maybe there was collision of the gripper or another issue. You can find description of these colors in our documentation. So you can find exact information what does it mean when your part has a brown color, and there are some recommendation what to do to have more successful beam picking. But we have very useful tool in our beam picking studio, which is called inspector. So for example, this part we can show inspector, and this tool will tell you exactly what is the trouble with this part. Now you can see, I will try to zoom it out and maybe move it a little bit, that for this part there is no way how to pick it out. Maybe if we will pick the green parts around, it will be moved itself, but this gripping point is not reachable for the robot, because your gripper is in collision with the beam. So maybe I can show you it like this, so we can see it. But I believe that after this part will be picked, this one and this one, then it will move down, and there will be some gripping point which will be available, and the path planning will be successful. So what can you see? There is a functionality which is calling the waypoints. So you can go through these waypoints and see each of the steps. So we can see that this is where the result is in collision gripper base with the beam right. So this is our right beam. So there is a collision with it. So in this part, you can see all the procedure which were called and when exactly were called. For example, there is 14.0520, the localization found 28 objects. The request for scan was received. We were waiting for localized objects, and so on. And then after the localization, the path planning was proceeded, and the path was sent to the robot. So robot was able to pick the object. The new feature in the beam picking is the cycle time, where you can see some overall average cycle time value. This cycle time is 37 seconds, which is really a long time. But for today, for the training, we slow down the robot to 20%. That you was able to see the movements with the robot, which corresponds with the deployment, with the visualization of the deployment. So that's why it is so long. And I'm just thinking if there's another maybe.
We can start the robot again and put it on a higher speed, so
we can
see the difference in the cycle time.
Yes.
Nice.
We paused the robot, so the cycle time is really long because of this pause. Okay. Okay. Maybe we can stop it because it's making a lot of noise. So now is not so you can see that the average cycle time is quite long because of this pause of the robot. But the cycle time here was 90 seconds because we speed up our robot a little bit. So we can just check it here, how it changed. So my colleague Patrick is on. Maybe would you like to say a few words about the new version of the beam picking? What are the key benefits? And maybe there is a question. So I will unmute my microphone and I will let you, Patrick, to answer the questions.
Thank you. Can you hear me? Thank you. We can get to the last question. Is there possibilities how to define another parameters of movement such as speed or acceleration? Actually, this is all defined on the robot controller. So Beam Picking Studio does not define any speeds or any accelerations, just the position of the movements. When you want to adjust the speed of the trajectories, you need to do that on the robot controller. This is all documented in our integration guides in the documentation. So all information you can find there. Maybe regarding the new features in this version of Beam Picking Studio, now we were watching the real live demonstration of beam picking using the actual robot. But as you can see on the deployment page, there are some new buttons available next to the stop beam picking and restart buttons that let you call the initialization request, scan request, or trajectory request directly from the deployment page. So if you want to just try the beam picking, the performance of path planning, you don't really need to start the robotic program. You can even disconnect the robot, turn it off, and you can call the initialization request with your preferred values of the start and end positions, and you can trigger scans and request trajectory. So you can tune the parameters, stop deployment, change some parameters, deploy it again, and see the difference. I think what wasn't mentioned is also the option to visualize, to display the volumetric model of the gripper. So Anna, if you could open the inspector for a part, you can see that at the bottom there is gripper model, and it's actually currently set to STL. Okay, please go to the invariance tab and try to. Okay, select a part, please. And now you can see that the gripper is represented by the volumetric model, which is the actual model with which we do the collision checking. So instead of the STL, you can display this model to have better insight to why the collision is happening. But in this case, you can see that only 0.06% of the gripper volume is in collision. So basically there is no collision. That is just the tip of the suction cup that is colliding with the picked part. So no collision is actually happening in the grasp breakpoint. Other feature that is new in the BIM Studio 1.6 is the ability to define multiple grasping methods. As my colleagues were saying, you can define different strategies how to pick the part, the approach waypoint, but you can actually have more vision systems, and for each vision systems, you can define unique grasping method. This can be beneficial in many scenarios when the parts are different, or when the pins have different shapes, when you need to define a unique picking strategy for each vision system. We have a new question. The scene is working exactly as walls, meaning the robot will always avoid running in collision with it. Yes, everything that is defined in the environment page as a collision object, I mean the cell itself, the gray base of the robot, the transparent walls, those are also collision objects. Also, the model of the scanner is a collision object, so it is a good idea to define a collision object around it just to be safe, but the actual model of the scanner is also collision object, so the path won't go through the scanner, so it is not possible to collide with the scanner or anything in the environment. And actually also the point cloud is a collision object, so if you put a hand under the scanner and trigger a scan, then the robot will navigate around the hand, or the patterning will fail. So there is actually no option to collide with anything that you can see on the scene. There were some previous questions regarding path planning and the messages in the console, for example, choosing object to pick timeout, which basically means that the timeout for path planning was reached and no trajectory was found. So in that case, you need to find the cause of the problem. Either it is the path planning that it failed, you need to find out why it failed, or the trajectory was requested at a bad time, because the timeout is usually 10 seconds. You can set it in settings, and if you call the trajectory request too soon, it might happen, because of the path planning, that the path plan won't be ready in time in the 10 seconds window. If the problem is that the path planning is failing, then you need to find the reason, and the reason can be found using the inspector. So you just click the part. Usually the regions are, the parts that are failing are red. As you can see, we have no red parts. Actually, we have only green and brown parts, and the brown parts means that the grasping angle is too high. The gripper would need to be tilted too much from the z-axis of the world coordinate system. Those objects will be pickable later when the objects around them will be picked. So the brown objects will fall down, will change their position and their orientation. So they will become green. And regarding the red parts, that means that the inverse kinematics in the waypoint failed. That is usually because of a collision with the beam walls or the point cloud. And when the patterning fails, that doesn't happen that much, because when the waypoints are computed, the patterning usually is successful, but it can happen, and then again you need to check the inspector and find the reason, and then navigate to the documentation. There are all reasons for failing described, and also some pointers on how to proceed, what steps you can take, what to check, what to change, and maybe you will find solution to a problem. A new question, good question. In the BIM Picking Studio box, a table with similar to a chessboard, black-white circles was included. Is this for any type of calibration you did not present today? Yes, BIM Picking Studio supports two types of calibration or the placement of the scanner. Today we presented the extrinsic approach, so the scanner was mounted on the cell, robotic cell itself, so the scanner is in static position. It is not moved during beam picking. When calibrating a extrinsic vision system like this one, we use the calibration ball as the calibration tool. The other object that is delivered when you order the beam picking studio package is the calibration pattern or a marker pattern. The chessboard pattern is on the marker on the tool, and it's basically just a flat paper with a pattern, and it is used for the hand-eye calibration. So when the scanner is mounted on the robot, we support scanner mounted behind the sixth joint. So basically with the tool on the sixth link of the robot. And the calibration procedure is pretty much the same. You just scan the calibration pattern that is placed inside the beam that cannot move. Hand-eye approach has many advantages, but also disadvantages. It is not suitable for low cycle times because during the scanning, you need to stop the robot. It cannot move because the scanner is on the robot, so you need to be static. But from the advantages, you can get closer to the beam, to the parts, so you have better details. That means better localization. So it all depends on the application, on your requirements.
Thank you, Anna. Thank you, Patrick, and thank you, Michal, for a great training. Just additional information, after attending the training, you have the special opportunity to buy a beam picking studio demo for the special price. So don't hesitate to contact us. And if you have any additional questions, please send them to sales@photoneo.com. Thank you very much for today. I hope you liked the training, and we are looking forward to the next training sessions and webinars about the Photoneo Robotic Intelligence, the beam picking studio. Thank you, and wish you a peaceful and nice day.